Now, something that neither Galileo nor Newton could have imagined is a chamber large enough that objects could be dropped from a significant height while all the air in the chamber was sucked out. But that's exactly what was done in this little video clip from a BBC Science series hosted by famous astrophysicist Brian Cox. First, you see a bowling ball and 3 feathers drop from the top of a NASA vacuum chamber with all the air present. And next, you see a slow motion drop from the chamber with all the air removed. And when you see the bowling ball and feathers plummet to the ground at exactly the same rate, even if it's in slow motion, it's quite astonishing.
Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest.
Now, the next video you're going to see is of an astronaut on the moon in 1971. Now, the moon has no air. It has no atmosphere like ours, but it also has a gravitational field that is weaker than ours. So when he drops the hammer and the feather, you're going to see them hit the ground at the same time, but it will look as though they're falling in slow motion, because when you're on the moon, you basically fall in slow motion.
Oh, wow, watch this. I have a good picture there. I've got
beautiful picture, Dave.
Well, in my left hand I have a feather. In my right hand a hammer. And I guess one of the reasons we got here today was because of a gentleman named Galileo a long time ago who made a rather significant discovery about falling objects in gravity fields. And we thought that where would be a better place to confirm his findings than on the moon. And so we thought we'd try it here for you. The feather happens to be appropriately a falcon feather for our falcon. And I'll drop the 2 of them here, and hopefully they'll hit the ground at the same time. How about that? It proves that Mr. Galileo was correct in his findings.
So maybe you're thinking by now, what's the big deal? Why is it important that this quarter, which is much less massive than this apple, falls to the ground at exactly the same rate? The reason is because it has something to do with how gravity depends on mass. Okay? We learned from the law of force and motion, from Newton's second law, basically, that acceleration is equal to the net force, in this case the force of gravity, divided by the mass. Okay. When a heavy object is pulled to the ground by a certain force, you would expect, because the mass is greater, that the acceleration would be less, right? In fact, if you got an object, say the apple, which is maybe, I should have measured it before the video, but let's say, just for argument's sake, it's 50 times heavier than the quarter. If it's 50 times more massive than the quarter, that means the acceleration should be 1/50th, because it's more sluggish. So if it's given the same force, it should accelerate more slowly. It's harder to get something going to accelerate it when it's more massive, right? But here's the thing. Gravity automatically compensates for this. In fact, I said the wrong word when I said the apple is 50 times heavier, because that's actually the force of gravity. It's 50 times more massive, but it's also 50 times heavier, because gravity compensates for the extra mass by making itself 50 times stronger. And 50 over 50 is 1. And when you multiply 1 by anything, it stays the same, right? And so that was the big idea that Newton got from this, from the falling bodies. He said, the force of gravity depends directly on the mass. The force of gravity is proportional to the mass of not only the objects that are falling, but also the mass of the thing that's pulling them, the Earth. Okay? And that's why it's important that objects fall at the same acceleration. So from the fact that falling bodies fall with the same acceleration, Newton found that the force of gravity must be proportional to the mass of the objects that are falling. But because gravitational force is between two objects, two massive objects, it shouldn't depend on one mass and not the other. It has to depend on both masses. Okay, so in other words, the force of gravity not only depends on the mass of the apple, it depends on the mass of the planet pulling on the apple. Okay? It not only depends on the mass of the hammer, but it depends on the mass of whether the Earth or the moon is pulling on the hammer. Okay? So this is a direct proportionality. If you double the mass, the force doubles. If we triple the mass or the force of gravity triples. That's why mass and weight are so often confused. Because if you increase your mass by 10%, you've also increased the force of gravity on you. In other words, you've increased your weight also by that same percentage. Okay? A couple of things that I've already mentioned that are worth writing down, though. Gravity of a spherical body acts as if all the mass is at the center. Okay, so we get pulled as though all the mass of the Earth is at the center of the Earth and is pulling us from a distance of around 4,000 miles. Okay. Also, gravity is universal. Everything that has mass attracts every other thing. If you're sitting next to another student in a lecture hall, or you're sitting across from a friend at a dinner, you are attracting each other. But gravity is so weak that only if one object is incredibly massive, like a moon or a planet or a star, only then is gravity really easy to measure and is actually noticeable. Okay? So those are some of the important things about gravity. And remember, when I say weight, what I mean is the force of gravity on a particular object. Okay? So, the law of gravity, the gravitational force, it acts whether the objects are touching or not. Okay, so I'm standing on the ground right now, and the Earth is pulling me. But if I jump up in the air, gravity still pulls me back to the ground. So I don't need to be touching. It is not a contact force. Okay, it requires two objects to interact. So even though the chair that's across the room is pulling at me, the Earth's pulling with a much stronger force, and that's the only one I feel. Okay, but any two objects that have mass are attracting each other with a gravitational force. It exists when any two objects interact. Okay? Any two objects in the entire universe are pulling on each other. But, and this is a good thing, it's significant only when one or both of the two objects are very massive, like a moon, a planet, or a star. It's also stronger when the two objects are closer together and weaker when the objects are far apart, and it weakens according to the inverse square law. Okay, so we have an actual equation. When we put these proportionalities together, we find that the force of gravity is directly proportional to the two masses and inversely proportional to the radius squared. But because gravity is such a weak force, if we put in the mass in kilograms and the distance in meters, we find that for regular sized objects in kilograms and meters, gravity is a ridiculously weak force. In fact, the proportionality constant is 0.0000010 zeros 667,428. Okay? On the next page, we're going to give this number a name and a symbol. The symbol is big G for the gravitational constant. Okay? By the way, it doesn't matter which object you call mass 1 and mass 2. The distance to the from center to center of the two objects is r. And again, it's called r not because there's a letter r in distance, but because it's usually a radial distance. So when you're talking about a planet or a star, or for example, you're talking about the force of gravity between the sun and the Earth, you would take the radius of the Earth's orbit, because that's the radial distance from the sun to the Earth. Okay. This is the number that's used no matter what two objects you use, and it's very small. At least one mass needs to be really huge to get an appreciable, measurable force. The units are such that when you measure this, you multiply by the two masses in kilograms, the kilograms squared go out, and when you divide by the distance squared, the meters squared goes out, so you're ending up with newtons, which is the proper unit of gravitational force, of any kind of force for that matter. Okay, so in another way of writing it, pretty much the same way, we've replaced that little number, 0.0000, okay, 10 zeros, 667, with big G. There's nothing special about big G, it's just that gravitational constant that makes the forces work out properly and makes the units work out properly. Okay? And 1 is the mass of one object. Could be the mass of a planet, for example. Mass 2 could be the other object, such as you standing on that planet. And r is the radial distance between the center of the two objects, such as the radius of the planet you're standing on. So this equation shows that gravity is proportional to mass and inversely proportional to distance squared. So in other words, when mass gets bigger, force of gravity gets bigger by the same proportion. Okay, if mass doubles, force of gravity doubles. If mass quadruples, force of gravity quadruples. If the distance increases, the force of gravity goes down, but it goes down by a lot because it's proportional to the distance squared. So basically the distance matters twice, okay, twice as much as the mass does. Right, let's do a little example with the inverse square law to understand this. Okay, let's consider two masses 1 meter apart, and we'll call the tiny gravitational tug between them F original, or F0, or F0. Okay, so here we have two masses, one then the other. Okay, mass 1, mass 2. And if we then separate them, let's say they're separated by 1 meter. If we separate them so that they're 2 meters apart, the force of gravity doesn't get cut in half. If life were fair, that would be great because that would be easy. But the force of gravity, it turns out, is proportional to 1 over the distance squared. So the force is going to be 1 over 2 squared times the original force. Or in other words, 1/4 of the original force. Okay? If we triple the distance from the original distance to maybe 3 meters, then the force doesn't drop to 1/3, it drops to 1 over 3 squared of the original force, or in other words, 1/9 of the original force. Okay? So basically, the force of gravity is very, very super sensitive to distance. Okay? This graph basically shows you this on the next page here. Unfortunately, this book uses D for distance instead of R, but you get the basic same idea. Okay? The distance between the center of the Earth and if you had an apple here would be its normal weight. Typical apple weighs about 1 Newton. Okay? At twice the distance, if you could climb up on a 4,000-mile high tower and you were twice as far from the center of the Earth, you wouldn't weigh 1/2 as much. The apple wouldn't weigh 1/2 as much. It would weigh 1/4 of a Newton. 3 times would be 1/9. 4 times would be 1/16. 5 times would be 1/25. That's how the force of gravity works with distance. Okay? We're out of time, so we'll see you in the next video.